So today we're going to have a look at using a pair of mutually orthogonal Latin squares of order 3 to decode the following using Olderogge's method. So I've got myself a message here that I've received. I've gone ahead and just split it into groups of 3 just for simplicity, but that's not always the case. And over here I have my two mutually orthogonal Latin squares. So I produced these in previous videos, and I've gone through the encoding process in previous videos too. So the decoding process is very similar to the encoding process, and I'm going to go ahead and create two arrays. My first one is called M, and the first 3 squared bits, 3 because of this, goes into the inside of the array. So these are our information bits. I'm just going to go ahead and put them in there. 101, 001 and 100, and in the encoding process we would actually calculate these, but we're going to go ahead and trust that these could be right. That's what we're going to check. So 000 goes down the side, 101 goes along the top. Okay, and final parity bits there go along here and here. So the first ones go down, so 0 0 0. Second one go along, so 0 0 0. We'll get to this last bit a little bit later. Okay, so we're going to go ahead and use these two Latin squares to rearrange these and place them in there. So if I go through, we go 0 down and 0 along. Well, that's just that one there. We go 1 down, 2 along, which is that one there. 2 down, 1 along. 1 2 1 is a 0. 1 down, 1 along, 1 down, 1 along is a 0. 2 down and 0 along, that one there. 0 down, 2 along is that one there. 2 down, 2 along is 0. 0 down, 1 along is another 0. And 1 down, 0 along is another 0. Quick check, I've got 4 ones there and 4 ones there, so while I could have made a mistake, the fact that they're the same is pretty good. So now what we're going to do is we're going to check each column and each row and see if we've got any mistakes. If we don't have any mistakes, then this is the code word sent, but that would be a pretty quick video. So 1 plus 1 is 2, under modulo 2, that is 0, so this column here is actually wrong, okay, because that should be 0, or one of these should be different. We'll find out. This one's quite correct, and this one is also wrong because that doesn't add up. So now let's look at the rows. We have well, that's correct. That gives us 2, which is 0 in mod 2. This is incorrect, so let's go for that. And this one's also incorrect. So I've got 4 errors there. Let's do the same for n very quickly. So that column incorrect, this column is correct, and that column is incorrect. And you can go ahead and check that them rows are all correct. So I've got 4 incorrect errors there, and 2 there. So I think the whole point of this method is you've kind of got to change 2 things. It corrects 2 errors. So if you can find a way to change 2 things in either the parity bits or the informational bits, it'll work out. Because I've got errors in both, that probably tells me that it's in the informational bits. So at this point it's just kind of like a puzzle. So what I could do, so we've either got this one and this one being incorrect, this one and this one being incorrect. So what I could do is I could just try changing them and see if this fixes n, and that's actually exactly what I'm going to do. So my first test, I could look at this one here, which was M02. I'm just going to make a note of that over here, and if that one was changed, then this one will be changed as well. So that will be M12. Sorry, that's M20. Whoops. And this is M12. So if I were to change them into zeros, that would fix this array, and then you've got to check it fixes this array. So very quickly, if I do that and I find 2 0 over in my orthogonal squares, 2 0 would be this middle one here, so 2 and 0, and that would go ahead and change this one. But that is part of a row and column that's exactly the same, so all that's going to do is ruin that really, and that's going to create more errors. So I reckon that it's probably not looking good. So let's try the other 2. We could look at this one and this one now. So this one is M10, and this one was M22. So again, let's look if that fixes M. N, sorry, not M. So 1, 0, let's find that in our orthogonal square, and it's probably this one down the bottom here. Look, 1, 0. So this one here would change to a 1 as well. That actually would cause this row to then be column, sorry, to be correct. It would break this row. But then let's have a look at this one. M22 is this bottom left one, so that looks good as well. So if I was to change that one into a 1, then that column would work, and if I change both of them to 1s, that row would work as well. So I think we have 2 errors in these positions here. So I'm going to go ahead and say, where was it? 1, 0. So this one here should be a 1, and this one here should be a 1, and that would fix these two here as well, and then they would both be correct arrays. And if I go ahead and write all of that out, then we can talk about that last bit just to check. So we would have 1, 0, 1, 1, 0, 1, and 1, 0, 1. There would be the informational bits in the array. Then I've got 0, 0, 0, 1, 0, 1, 0, 0, 0, and 0, 0, 0. Now, just to make sure this is correct, if this was correct, then the overall parity of the code word should be even. And I've got 1, 2, 3, 4, 5, 6, 7, 8 ones, which is definitely even, so that 0 on the end is correct. And therefore there was only 2 errors, which means this is my received code word. And yeah, I'm done.